So yeah, as Fedor has mentioned, I'm Lezcano. I've been a PyTorch co-developer for the last 3 to 4 years, and in the last year and a half, I've been working on torch.compile and the whole torch.compile stack. So this talk is going to be a little bit of an introduction to torch.compile, and in particular, like what's happening behind the scenes, and like how can you introspect it. Like you have your program, perhaps like you run it and it's faster, perhaps it's not. If it's not, like, what do we do about it? If it's fast, can it be even faster? So how do we are going to be looking at different things that the torch.compile does, and in particular, like, how can we actually look at that in different programs? So first of all, what's torch.compile? Torch.compile is a compiler, just-in-time compiler in particular, that was added in PyTorch 2.0. It was a major feature from PyTorch 2.0. There was a good 1 year between the previous release in 1.13 and 2.0, and that whole year there were like a good amount of people working on torch.compile to deliver it. Then torch.compile is a compiler that can trace through arbitrary Python code. It's not, and it's well, we're going to discuss more about that, but it's a tracer, meaning that like it does not. There's two types of two ways of doing this. Like there's the way that Torch script used to work. Like I'm sure that many of you have fought against Torch script, where you have something that is like a DSL, a domain-specific language, and then if you write everything in that language, then the compiler knows how to understand it and optimizes. TensorFlow is another example of a DSL approach. Then there are tracers where you give it some inputs, and it will use those inputs to go through the code and trace through the code and generate a trace. Where torch.compile is the latter one, and we are going to talk like at length about this tracing stuff. It can handle mutations and views, as opposed to, for example, JAX, where everything is contiguous and everything is non-mutable. And it compiles, and at the end, like it compiles generic PyTorch programs written in Python into C++ with OpenMP for parallelization, and then onto Triton for CUDA. Triton is a library by Philip Tillet, a guy at OpenAI, that basically allows you to write very efficient CUDA kernels fairly easily, let's say. Much, much easier than writing CUDA, that's for sure. This is just a tiny example where we have like just a very small program that does interpolation between x and y, given a vector of weights. And here on the right, we see what we get when the last line is executed. Like when you tag something with torch.compile at the beginning, what that means is that you will want that thing to be traced, but nothing happens there. Like, well, there's some things happening in the background, but it's very, very fast. The actual compilation and the actual tracing and everything else happens in the last line. For this particular program, the C++ code that we generate looks like this, or so. Like, it's actually a little bit more difficult to understand than this because we perform a number of the optimizations. In particular, we do things like automatic vectorization and things like that. But it's pretty much this. It's a for loop where you take like the 3 input pointers, you iterate in a for loop through all the elements, and then you load the elements, perform the operations, and store the elements. Why is this better than eager PyTorch? Well, it's better because loading like point-based operations are actually very cheap when performed by the CPU. Like most of them take, when vectorized actually, they take less than 1 cycle. You can perform quite a few, like, you know, 4 point-based operations in 1 CPU cycle. But loading things from memory and storing things into memory is really very slow. Rule of thumb is like between 50 and 200 times slower than a point-based operation. So by doing this, what we do is like we are just loading all the data once. We perform all the operations on registers on our CPU, and then store it, and we're done. On the other hand, on PyTorch Eager, what we do is that we end up having like 1, 2, 3, 4 operations, and for each of those operations, we will load the inputs, will perform the operations, that particular operation, we will allocate the output, and we will write to the output. That basically means that, like, just roughly in this program, I haven't benchmarked it, but I would say that in this program you would get like between a threefold, or between 2 or 3x speed up in this very simple program. So that is torch.compile. That's what it does. But like, how does it do it? That is what we're going to discuss today. By the way, if you saw in the previous slide, I put there at the very top on the right, torch logs equals output underscore code. This is an environment variable, where we are going to talk a lot about different torch logs. Like if you run your program as says that with that environment variable, like torch underscore logs equals output underscore code, Python, and then your script, then it will output things. And that is the way that we will use to introspect what's going on behind the scenes. I will show, like, I will have this thing where I have a Python program, and then I have some output on the right, and then at the very top of the slide will always be what is it I'm using to generate that output. Usually the outputs will be much more verbose. Here, like, I've just trimmed them quite a lot, and I'm so that you just get, like, I'm directing your attention to the things that are important. But like when you see those logs, you see many more things when you run those logs with your program. So first of all, if you run any PyTorch program with torch logs equals help, you will see all the options that you can pass it. There's like a good 20, 30 options to see everything and anything that happens during a compilation. So you can even do torch underscore logs equal plus help, which will give you even more options. So yeah, plenty of things to play around with there. Here we're going to explore just a few of them. So the compile stack. Torch.compile has 3 parts. Dynamo, which is a Python tracer. Then there is a second Python tracer. Well, it's actually a second tracer, not a Python tracer, that is called AOT Autograd. That is short for ahead of time autograd. And then there's the actual compiler, Inductor. We are mostly going to be talking about the first one because it's the more difficult one. The other 2 are, at least conceptually, easier to understand. I have slides for the last 2. If we have time, we'll mention a few things about the second tracer and the compiler. But we're going to spend most of the time talking about Dynamo. So, all right, what's Dynamo? Well, first of all, it's a Python tracer. Given some inputs, so it's not a DSL. It doesn't understand all of Python. You need to give it some inputs, and given some inputs, it records all the operations that happen on PyTorch sensors. So in this case, when you execute the last line, the MSE XY, it executes, well, it basically will execute the program, and it will record all the operations. It will record them into something that's called an FX graph. FX graphs have been in PyTorch core since like PyTorch 1.7, I want to say, and they are just a list of functions. They are nothing but a list of functions. Here we see that we have like a subtraction, a squaring, and a sum. They are a list of functions, and the point here is that there is no branching, there is no funny business, there's just one function after the other that just takes the outputs from any of the previous functions and feeds them into a new function. That is an effective graph, there's nothing else. And the particular thing that you need to remember is that it's linear. There's no branching whatsoever. So Dynamo is something that goes from a PyTorch program into one of these FX graphs. Now, how do we do it? Like, well, this program is very simple. Like, there's just a few operations. It recorded it. That's fine. Like, how difficult could it be? But has anyone here ever used if-elses? Well, that is a problem. If we have if-elses, well, we don't have one branch. We have 2 or many. And what if we have while loops? And what if, we have said here that torch.compile can trace any Python function. So, in Python, you can implement many things. You can even implement a video game you want. So, can it trace through a video game? I don't know. Let's have a look. So first of all, it's a linear traces, as I've discussed. Like it completely removes any control flow operations, like if else's, loops, exceptions, any that it removes. It will just give you a linear trace. And it also specializes all non-tensor objects. In this case, we have an integer, but we see that when we parse we trace through the function, the 2 was baked into the graph. And it was baked not as a 2 plus 1, but just as a 3, because it is the way that it interacts with tensors, in this case, y. It's very nice that when you, again, top right, torch logs equals graph code to see this sort of output, which is the output of Dynamo. You can also, if you have a look at help, you can also look at the torch logs equals Dynamo, which gives you this and many, many other things from Dynamo. So linear traces removes all control flow and specializes all non-tensor objects. You have strings, it will get rid of them. Just things that interact with tensors will be recorded. Well, not quite. It actually knows how to trace integers as well. So you see here that I called, after the first function, I called it a second time with a different integer. And then when we run graph code, we see that it generated the graph before, the one from the previous slide, but now it generated the second one in the second call. And this second one, it's a second different trace where basically it's detected that you have changed an integer in your program. It's like, all right, so you may want to change this integer, so let me trace through it. And now we get a slightly modified function that doesn't take just one tensor, but it takes what's called a cement, symbolic integer. So these symbolic integers record all the operations, same as tensors, record all the operations that affect them, and add them into the graph. Why would we want to trace integers? Well, so something that's an integer is the shape of a tensor and the strides of a tensor. Particularly the shape of a tensor, imagine that you want to run your model in production with many different batch sizes, because sometimes you have like different workloads. How would you do that? If you would need to compile. You would need to compile, if you don't know how to generate code that is generic on integers, you wouldn't know how to generate a code that can handle any batch size. What you do nowadays is you usually just compile all the powers of 2 of the batch sizes and then pad the inputs and so, but that is not great. It's better if we know how to trace through things properly. And also another case of this is like, all right, arbitrary length sequences. Like you might want to have a model that knows how to handle arbitrary length sequences. So, but you also want to compile it. So this is what symbolic integers allow us to do. In general, Torch Dynamo, what it does is what we call static by default, which is the first time it will bake in all the integers. But if any of the integers changes, like you have passed to a function something that first had this shape, and then like you've changed one of the shapes, one of the dimensions, that dimension will be marked dynamic and it will be traced symbolically, similar to this n number here that we have changed between the first call and second call. So something else, well, we discussed that there's if else's. So how does Dynamo do to be sound? Meaning that like, sure, it linearizes the program, but programs are inherently non-linear. So how does it handle that? Well, it handles that. Here in this case, we see that we generate when we run this code with graph code, we see that it emitted the n equals 2 code, n greater than 0, so greater or equal to 0, and then in x equals 6, it doesn't emit anything because it can reuse the n greater than 0. But then when we pass n equals to -3, it retraces automatically for us. How did it know? Well, it does this retracing via something that's called guards. Guards is a concept in compilers that actually Python, like CPython also uses behind the scenes from 3.12. Guards are just Boolean expressions that depend on the inputs of the function and global variables, actually. Like all the L's that you see here stand for local. If you use global variables, you'll see a G. So guards are created, accumulated during tracing time. And what they mean is that if you generated guards, we generate guards whenever there is a split. Whenever we may not do the same thing if the inputs were not the inputs that we have. In theory on compilers, we call these preconditions. So we create a set of preconditions, a set of guards, and those are installed in the function. And the first thing that the function does, like you trace, you compile, you do whatever. And then like when you give another input, like you evaluate all the guards on these inputs. If the guards are true, then it means that we don't need to retrace. So we can just reuse the previous thing that we had compiled. But if the guards are false, then we need to retrace. So here we see how, well, first of all, we now know, we now see here how to recompile when there was a 3. Because, well, the first guard is like n is equal to 2. We pass the 3 is certainly not equal to 2. And then if we, like, again, torch log equals guards, tell us the guards, and equals recompiles, and you can pass a 2 with a comma, recompiles tell us the reason why it recompiled. So in this case, it tells us that it triggered because like the n equals 2 guard failed. It's here. Actually, there are many, many more guards because like we got on like global state from PyTorch and many other things. But it tells us that the one that failed was this one. It was not equal n equals to 2, so it installed a different guard, which is n greater or equal to 0. And then in the second, when we call the -3, it tells us that all the other guards, it evaluates all the possible guards, because it could be that you have an if else, if else, if else, if else. And in that case, you could have like plenty different things already compiled. So you need to pattern match pretty much. And if any of those happen to be true, then you can reuse that branch. Otherwise, if all the possible guards fail, then I'll need to retrace. In this case, with the -3, we need to retrace, and we get the other branch. So guards are the mechanism through which Dynamo and torch.compile makes for a sound transformation. Now we go for completeness. We said we can trace anything from Python, but Python is huge, of course. Like you can implement pretty much anything with Python. So we are, like in all fairness, we are not going to be able to support all of it. But what we want to do is we want not to fail. That's the important part. Like all the approaches before, and again, like I'm sure that most of you have used TensorFlow, JAX. They really, like when you don't write the code the way they want, they yell at you and they refuse to compile. We didn't want to do that. We wanted to have something that reflects the dynamic part of PyTorch, which is like, you give me something, I'll compile it. And it may not be the most efficient part, but like that's how you should actually write code always. Like you should have something that works and then iterate to make it faster. Like you shouldn't try to be thinking about optimization from the get-go. I mean, you should a little bit, but like not to do things from the very beginning. So here we have an example of something that we don't know how to handle, because like it has some what's called a side effect. It's printing something on the screen. So here we have a square, we print the result on the screen, and then we divide that by 2 and return. There's no way that we are going to be able to do that at compile time. Like, because y, we don't know at compile time what's the value of y. We wouldn't be able to print it. So what we do is we graph break. Graph breaks are basically the way that Dynamo has, like Dynamo is playing a game with CPython. CPython is the main Python implementation, the standard Python implementation. Dynamo is playing a game with CPython where Dynamo tries to trace, well, it asks CPython to execute the code. It executes the code as much as it can. It finds something that it doesn't understand. It gives it the ball back to CPython and stops tracing. And then like that wraps up that graph and puts it aside, and then CPython will execute that instruction that we didn't know how to execute, and then we will go back to, it will return the control back to Dynamo, and then Dynamo will continue tracing, and we'll do the same thing over and over and over. So Dynamo doesn't generate necessarily just one graph, it may generate many different graphs if there were graph breaks. In your code, you would want to have like as few graph breaks as possible, because you would want to have like a very, very large graph that that encompasses all your neural network, because that way the compiler will be much more efficient, and because it has access to the whole graph. So you can have a look at torch logs, graph breaks, and explain, and it tells you that in this case, well, you try to call a function which is called the built-in variable print, that's the name of the function, with a tensor, those are the arguments, and no keyword arguments. That's why there's an empty dictionary there. And then explain says that that was in line 6 of the file that I executed, which also has a torch import over there. So that's why it's line 6. So this is the way that that Dynamo uses to be able to support all Python. So to summarize, Dynamo is a linear Python tracer that, given some inputs, it creates an FX graph with the PyTorch operations that happen during that trace. It specializes all non-tensor values, but also is able to trace integers symbolically whenever it needs to. It uses guards to decide when it needs to retrace, and it may fall back to CPython when it finds construction that it doesn't understand. That is the whole part of the tracer. Now let's talk very quickly about the two other parts, because I don't think I have much time. So AOT Autograd, second tracer, what does it do? AOT Autograd does 3 things. It takes the FX graph, we saw that Dynamo can create plenty of FX graphs, but AOT Autograd will act on them individually. So we can think of it as like, all right, so what does it do in one graph? It does 3 things, actually. It's going to generate the second FX graph, but at a lower level. Like, it's going to decompose things into more basic operations. It's going to perform what's called functionalization, which is like it will remove all the in-place operations, and we'll see how it does that. And then and the name AOT Autograd, ahead of time Autograd, comes from the fact that when it was first implemented, it was it was first built just to, given a forward graph, compute the backward graph that computes the gradients of that forward graph. So it does those 3 things. The third one is quite obvious once you know how to compute gradients. So let's talk about the other 2, which might be a little bit more tricky. So the first one, So here is an example of an AOT graph. We can see it with torch logs AOT graphs. So here we have a very simple very simple operation that does something like it returns x if x is greater than 0, and otherwise it computes the exponential -1. This is an activation function that we have in PyTorch. So when we trace through that, well, first of all, PyTorch has a good over 1,000 or 1,500 operations in it. So it would be absolutely mental to try to write a compiler that knows how to handle all of those. So what we do is we decompose all those operations into about 200, that we say that those 200 operations are core operations. And then the compiler will just need to know how to handle those 200 operations. So in this case, we saw the decomposition over there, and here we see on the right that we have another FX graph that has a few other things, that also has types and also have sizes, that calls these agent functions. GT for greater than, xpm1, this is a C++ function that computes exponential -1, and then where, which is the backend for TorchWare. So what is A10? A10 is actually the library that we have within PyTorch that implements PyTorch. It's the library that's written in C++ and CUDA, and the Python frontend is just a frontend for this A10 library. So here, it just calls directly those operations, and that is the IR, the internal representation that we use within torch.compile, within inductor, actually. This afterwards, the compiler. And the second part is functionalization. What if we want to perform the activation in place? So compilers hate, like really, really hate in-place mutations. If you are using torch.compile, please don't use in-place mutations. Like, let the compiler perform those optimizations, because like it's very, very, very reasonable, very difficult for a compiler to understand the mutations and reason about mutations. So what it does, it completely removes mutations, and it just adds at the end a few copies to preserve the semantics, and it will let the upper graph that we see there. It's what we call the functionalized graph, and it's the part that will be compiled. And then at the end, we will add a few copies that will not be, like those copies will not be seen by the compiler. They will just become part of the final program. And here I had some notes on like a few things that Inductor, the compiler, has, but I think that we might as well just finish here, and we can already take questions, if there's any.